Okay, so this video is going to be about hypergeometric distributions. It's kind of like binomial distributions, but slightly different. So if you remember, binomial was, so the conditions were that we needed repeated trials, and then we had to have, it had to be two possible outcomes. So it had to be a two-outcome trial, which we would describe, of course, as a success or a failure. And the third thing is that it had to be independent. Now what's going to change here, of course, not of course, what is going to change here is that hypergeometric distributions are going to be dependent trials. So it's going to be, and in particular, it's going to be when you have essentially a pool of successes and failures. So hypergeometric is essentially a situation. You have your pool, and you have all your, successes, and you have your failures. And we're going to be reaching in and pulling things out of the pool. So right now there's 1, 2, 3, 4, 5, 6, 7, 8 successes, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever, 12 failures. And when we remove a success from the pool, there's one less success available to be had, which is going to change the probability. So that's going to be a hypergeometric distribution. We're going to go right to an example. So a bag contains 14 marbles. It's going to be 6 green and 8 red marbles. We have 6 green marbles and 8 red marbles. And then what we're going to do is we're going to draw 7 marbles from the bag. Without replacement. So that means after we draw it, we will not be putting it back. This is different than binomial, where we would take it out and then put it back in to keep the probabilities the same. And so the question is, or at least the first question is, what is the probability of pulling exactly 3 green marbles? And we've actually already done questions like this. In fact, I don't think we're going to be developing a formula, but I actually don't think the formula is that useful for this. But for some people, it will be. So I am going to be showing it because I am supposed to be showing it. It's a little fuzzy day thing. Why is it not focusing? Oh, well, hopefully my words will do it with the blurriness. So what's going to happen is, so we want to know what is the probability of pulling exactly 3 green marbles. So our NS is pretty straightforward. Our NS is, we have 14 marbles, we're pulling 7 of them. There's 14 choose 7 groups that we could pull. For the NA, what we want is we need 3 greens, and we need to get 4 reds. And the probabilities for those guys are, for the 3 greens, there's 6 greens, so it's going to be 6 choose 3. For the 4 reds, it's going to be 8 choose 4. And so my overall probability, the probability of 3 green, is going to be 6 choose 3 times 8 choose 4 over 14 choose 7. And that's that. So kind of the same idea, what we do with binomial, we're going to create a formula out of it. So what we're going to do, I should probably leave that paper close by. So we're going to say the variables used. So what we're going to say is that n is the number of trials, a is the number of, what color did I use for successes? Whatever. The number of successes in the pool. T is going to be the total possible outcomes. And X is going to be the number of successes. I'm going to pause here for a second. I don't write this down, but if you have a copy of the textbook, they actually use different variables. For number of trials, they use R. For successes, they use A. For total outcomes, they use N, and this is X. And they have a reason for it, but I think it's a lousy reason, and it's confusing because here N is trials, and here R is trials, and here N is something different, and I think it's just a big mess. So I'm actually not going to be using these variables, but if you're using the textbook and you want to use the book's variables, that's definitely fine. Okay, so going back to our example over here, the number of trials was 7. We pulled 7 things out there. Actually, I should say what a success is first. So success is pulling a green. So there's 7 trials. The number of successes that are in the pool, they're, so we're saying success is a green, and there's 6 greens available. So that's going to be 6. T is the total possible things in the pool. So that's going to be 14. And the number of successes we're looking for in the example was 3. And then if you remember, it was this thing over here. So it's going to be, so our formula is going to be the probability that x equals 3 or x equals x is going to be 6 choose 3. So it's going to be 8 choose x times 8 choose 4. So 8 was this minus this. So t minus 8 choose. And then 4 was the number of trials minus the number of successes. So we're counting how many failures we have. So it's going to be n minus x. All divided by 14 choose 7, which in this case would be t choose n. And that's going to be the formula for a hypergeometric distribution. So let's do an example with it. So we have a full deck of cards. 10 cards are drawn. What is the probability? Exactly 4 will be hearts. So we're going to set it up. So what's a success? Success is going to be draw a heart, like pull a heart out of the deck. And how many trials do we have? We're drawing 10 cards, so that's going to be 10. The number of successes, so if I'm saying success is a heart, how many hearts are in a deck of cards? There's 13 hearts in a deck of cards. Total, the total of outcomes in the pool, each card is an outcome, so that's going to be 52. And the number of successes we're looking for 4 successes. So then the formula is going to be the probability that x equals 4 is going to be 8 choose x, so 13 choose 4 times 52 minus 13, choose 10 minus 4, over 52, choose 10, or 13, choose 4, times 39, choose 6, over 52, choose 10. And then we get our fancy calculators out, and we get 13, choose 4, times 39, choose 6, divided by 52, choose 10. So it's going to be 14 point, almost 8, but 14.7%. And again, you don't have to do you don't have to use the formula if you don't want to, but you can. Okay. I'm going to pause here and do expectation in the next video.